Hi, everybody. We're on the air, and now we're doing 7.2 diagonalization. So, what does that mean, diagonalization? So, we learned about, first, we learned about similar matrices, and we learned that two matrices are called similar if you can find an invertible matrix P that B is equal to P inverse times A times P. So, if this happens, then A and B are called similar matrices. And um, So we did this back in chapter 6. I'm sure this brings back pleasant nightmares for all of you. Now, if you have a matrix which is similar to a diagonal matrix, then we call that matrix. Then we call the matrix diagonalizable. I can never pronounce that word. Diagonalizable. So an n by n matrix is diagonalizable when A is similar to a diagonal matrix. That is, A is diagonalizable when there exists an invertible matrix P such that P inverse times A times P is a diagonal matrix. And just to refresh your memory, a diagonal matrix is where you have all zeros except for the main diagonal, but everything else is zero. That's a diagonal matrix. Anyway, so here we have an example. If you have A as our matrix, now A is not diagonal, but we're saying that A is diagonalizable because if I would take the matrix P, now when I say I really mean you. I want you all to take the matrix P, figure out P inverse, which you all know how to do that, and multiply P inverse times A times P. And if you do that, you should get this guy right here, which is a diagonal matrix. Because you see, it's all zeros except for that main diagonal. And I'll just highlight that main diagonal so you see what I'm talking about. It's one. So notice these are all so these are all so there you go. So this is diagonalizable. Okay. So let's see if we can let now. Now I know you're all thinking, gee, gosh, golly, what does this have to do with eigenvalues and eigenvectors and all that kind of stuff? Well, guess what? We're gonna find out. So similar matrices have the same eigenvalues. That's a very important and fascinating formula. It's not even all that hard to prove. We're gonna prove it right now, in fact. Similar matrices have the same eigenvalues. So let's see why that is. So if A and B are similar, that means you could find the matrix P where B is equal to P inverse times A times P. And we want to look at the determinant of lambda I minus B, which is something relevant, which, as you know, is something that's relevant to eigenvectors and eigenvalues and all kind of eigen stuff. And we want to look at the determinant, and let's do some math magic. So first of all, since we're going to replace B, since B is equal to P inverse AP, we're going to substitute P inverse AP for B. So that's our first step. Then we're going to take this lambda I and multiply it by P inverse on the outside and P on the other side, because that's still gonna be equal, because lambda I is just the identity matrix with a lambda on it. If I multiply it by P inverse and P, it all just cancels out to be the same thing. Now I'm going to do a double kind of factorization, because remember, matrix multiplication is not necessarily commutative. So I can factor out the P inverse because they're both on the left side. I can factor out the P's because they're both on the right side. So I get that this is equal to P inverse times lambda I minus A times P. Now, the determinant of a product is equal to the product of the determinants. So I'm going to separate this into three separate determinants. But we all know that the determinant of P inverse times determinant of P is equal to 1. We learned that the reciprocals of each other. And you can see from right here, because if I would combine them into one determinant, I get the determinant of the identity matrix, which of course is just equal to 1. And now I'm left with lambda I minus A. So I've shown that lambda I minus B, the determinant, is equal to the determinant of lambda I minus A. Well, that means that A and B have the same characteristic polynomial, so it means they have the same eigenvalues. Because the characteristic polynomial comes when I set these dudes equal to 0, and it must be the same characteristic polynomial because the two, it's all good. It's fabulous and wonderful. It's amazing and similar. So we see right away a connection. Now we haven't gone to diagonal matrices exactly yet, but diagonal matrices and similar matrices are definitely combined. But it's going to get better and better. It's going to get better and better. So we want to find eigenvalues of similar matrices. Well, the matrices A and D are similar. Now, why are they similar? How are they similar? That's another story. But actually, on the side, it kind of will explain it. But before we'll do that afterwards. But let's just do the problem that they're asking. What are the eigenvalues of A? Well, the eigenvalues of A are going to be the same as the eigenvalues of D because they're similar. And we know that the eigenvalues of a diagonal matrix are just the elements of the main diagonal. So therefore, the eigenvalues of A are going to be 1, 2, and 3. And pow, we are done. And now we want to what we like to do to check this is to take the characteristic polynomial of A. If you do that, you're going to get lambda. If you do it, you should get, if you do it right, lambda minus 1 times lambda minus 2 times lambda minus 3, which is exactly what you would get for this guy. So you'll see that it's actually true, but I want you to do that on your own. This example, now, so we're claiming that A and D are diagonal, but here on the side, it shows us the P that's going to work to make it, because I want you guys to verify that these two matrices are indeed inverse is of each other, and if I multiply P inverse AP to this A, I will get that D. So I want you to verify all this stuff. That's something you can do just through regular multiplication, and it's all cool. Okay, let's go to the next. Next, we have a condition. Next, we have a condition for diagonalization. Whoops, went too far. And that is that an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. That's really cool and interesting. So if the eigenvectors, if there are n, because you're not always, an n by n matrix will not always have n eigenvectors, and will not always have n linearly independent eigenvectors. Really better with that. And but if it does, then it will be diagonalizable. So that's pretty cool and awesome. Let's go through the proof. Very awesome, very cool. So first, we're going to assume that A is diagonalizable. Then there exists an invertible matrix P such that P inverse A P equals D, and D of course is diagonal. That's what diagonalizable means. So let's look at the column vectors of P. We're going to call that P1, P2, Pn. Those are going to be the column vectors. And the main diagonal entries of D is going to be lambda 1, lambda 2, dot, dot, dot to lambda n. Now, I want to look at PD. PD is this. Now, this is not a vector. This is a whole matrix. It's just that P1 is an entire column, P2 is an entire column, dot, 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 Pn is an entire column. Now, when I do this matrix multiplication, because of all the zeros here and everything, what's going to wind up happening is that the first column, now this here is an entire column. The first column is going to be lambda 1 times the first column of P1. The next column is going to be lambda 2 times the P2, and so on and so forth. And that's what I get. That's going to be my PD. Now, PD, oops. So now P inverse A equals P inverse AP is equal to D. which means AP is equal to PD. I just multiplied both sides here by P on the left side. Now, if AP equals PD, well, we know PD is this guy over here. We just did that. We just showed that a second ago. AP is going to be this guy over here, by a similar argument. Well, that means that AP1 is going to equal to lambda 1 P1, AP2 is equal to lambda 1 P2, dot, 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 APN is going to equal to lambda n Pn, which means that the column vectors Pi of P are eigenvectors of A, because that's what an eigenvector means. That's the definition of an eigenvector. Now, because P is invertible, the column vectors are, drumroll please, linearly independent. Because any invertible matrix has to have linearly independent columns as well as linearly independent rows. Right now we're just talking about columns. So A has n linearly independent eigenvectors, and that's what we just showed. And that is awesome. Awesome. Now let's do the other direction, the converse. Converse means the flip side, the other way. Assume that A has n linearly independent eigenvectors. Well, the converse is really going to be kind of the same as the original thing. We're just going to do everything backwards. The converse is really just going to be doing everything backwards. Let's go through it. So we're going to assume that A is n linearly independent eigenvectors, and the eigenvectors we're going to call them very conveniently P1, P2, Pn. And they're going to have eigenvalues lambda 1, lambda 2, lambda n. Now, since let P be a matrix whose columns, you ready for this? What a shock, are these n eigenvectors. So I'm going to take these n eigenvectors and turn them into columns of a matrix. I'm going to call that P. Oh, whoa, that's amazing. So basically, we're going to show that this P has the properties that we want it to have. Now, because each Pi, each individual column, is an eigenvector of A, so we know that matrix A times column Pi is equal to lambda I times column Pi. So AP, which is equal to this guy, is also equal to that guy, but that guy there is PD. So we have AP equals PD, and because these vectors are independent, that means P is invertible. So I can multiply both sides here by P inverse. I get P inverse AP equals D, which means that A is diagonalizable because A is similar to a diagonal matrix, and that is awesome. So these last two theorems I just showed you will be absolutely awesome, improving a lot. And a very huge result of the proof is the fact that for diagonalizable matrices, the columns of P consist of n linearly independent eigenvectors. That is very awesome and very important. And let's look at example 3, which is going to verify this. Let's look at example 3. So I have a matrix A from example 1, and has the following eigenvalues and corresponding eigenvectors. So lambda 1 is 4, and P1, which is an eigenvector, is 1, 1, 0. Lambda 2 is negative. For lambda 2, negative 2, P2 is the eigenvector. Lambda 3. Now, let's just look at example 1 just to remind ourselves what it was. And that was example 1 right there. So example 1 was this guy right here. And notice we said 1, 1, 0, 1, negative 1, 0, and 0, 0, 1. So that's kind of cool. So that's example 1. And let's just go back to the problem that we were doing, example 3. So the matrix whose columns correspond to these eigenvectors, but if I take these 3 eigenvectors, just stick them all side by side next to each other, is P, which is the matrix that we saw that matrix up in example 1. So because P is row equivalent to the identity matrix, the eigenvectors are linearly independent. That is awesome. Let's look at another matrix A in example 2 has these eigenvectors and values. Remember that was a 1, 2, 3, 1. So the eigenvalues were 1, 1, 1, 0, 1, 1, and 0, 1, 2. And we saw these eigenvalues, we saw these we saw that in the left side column when we did example 2. Let's take a quick look at it. Oops. That's what we're talking about. We're talking about this guy right here. So so that is awesome. And oops. And so again, P is row equivalent to the identity matrix. I mean, since it's row equivalent, then the eigenvectors are linearly independent, and that is awesome. Because any yeah. Okay. So I want to, let's see, how long have we been on this so far? Well, everybody, now we're going to show how to actually diagonalize the matrix. Means if we give you a matrix now, because you said, okay, here's a matrix, and we gave you all the eigenvectors and eigenvalues and diagonal. We did all the work for you. We just asked you to verify everything. But now we're going to actually show you how to find how to diagonalize the matrix, and very important skill, and it's something that we already kind of like, we're just gonna kind of follow what we just did already in these last proofs and stuff. That's why these proofs are so important, because they give you a lot of techniques and stuff, and they just help you understand everything, give you more context. It's really important. Proofs are not a some people tragically, I see students all the time who view proofs as a pain, but actually proofs gives you an insight and a context of what's going on. Anyway, so here's the steps for diagonalizing an MBN, a square matrix. So you want to find n linearly independent eigenvectors. Find the eigenvectors, that's something we trained how to do that, if possible. And you want to find the corresponding eigenvalues. And if these independent eigenvectors don't exist, well, then we're done, because it's not diagonalizable. But if they do exist, find them and the eigenvalues and eigenvectors, and then take all these vectors and stick them, press them all together into one giant matrix P, which is P is column P1, P2, Pn. These are all, this is a big square matrix, because P1 is a whole column, P2 is a whole column, Pn is a whole column. Now, the diagonal matrix D, which is equal to P inverse AP, will have the eigenvalues lambda 1, lambda 2, lambda n on its main diagonal, and of course, the zeros everywhere else. But note that the order of the eigenvectors used to form P will determine the order of the eigenvalues, because they're going to correspond to each other. But so that is that's the beautiful. So if I can find the eigenvectors, which we've already learned how to do that in 7.1, I could use that to find the P, construct the P, which will give me my diagonal edges, and that's how I diagonalize a square matrix. So let's do an example. So let's see, here's a matrix A. So we look at an example now. We want to show that A is diagonalizable, and let's diagonalize it. So here's my matrix A right here, and we want to find a P that's going to make this diagonal. Now the characteristic polynomial of A, if you were to crunch this all out, and again, I want you to crunch this all out. If you crunch out this determinant, you're going to wind up getting lambda minus 2, lambda plus 2, and lambda minus 3. And again, I want you to do it. So the eigenvalues of A are going to be 2, -2, and 3. That's going to be lambda 1, 2, and 3. Now, from these eigenvalues, we can figure out the row-reduced row echelon forms, and we can find the corresponding eigenvectors. So when I put in the eigenvalue when I put in lambda 1, which is equal to 2, I get 2i minus a, which gives me this, which I can row reduce to that, and that's going to mean that x2 is going to equal 0, and if x3 is t, then x1 will also be t, negative t, I'm sorry. So that's why you get the eigenvectors -1, 0, 1. And if lambda is -2, I get this matrix, which reduces to that. Again, I want you to crunch all this out and see that you get all these and then this will give me, again, if I let if I this is going to lead to this eigenvector through a similar method. And if I use lambda 3, which equals 3, I get 3i minus a, which gives me this matrix, which then I can row reduce to this matrix. And if I let x3 equal to t, but over here I let x3 equal 4t, just made it a little bit easier. And then once it's 4t, then that became t, and x2 became negative t. That's how I get the -1 here. But here I'm letting x3 equal to 1, so that makes x3 is equal to 1, so x1 is also equal to 1, and x3 equals 1, so x2 is also 1, and x1 up here is -1, which is how I get this guy right there. Now I take these three vectors, sort of, tape them all together, and I get this matrix P, and P is going to be, P is going to do the trick. This matrix P, if it's invertible, which again I want you to check that, and the eigenvectors are linearly independent, and therefore it's diagonalizable, and so that means that P inverse A times P is going to give me this guy right here. But again, I want you to show that and actually crunch it all out, and you'll see it's all true. And once you do it, you'll realize how awesome all of this is. Let's do another example. Let's do a 4x4, and here we go. So we want to diagonalize this. So we saw this matrix already in example 6 of the previous section, and we found that the three eigenvalues are lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. And they have the now lambda 1 had two different eigenvectors, two independent eigenvectors. Lambda 2 has this guy, and lambda 3 has that guy. And this example again was in the previous section. So all that work was done, but you should make sure you know how to do it. And now I take these four matrices, and I just tape them all together, just crunch them all together, press them all together into one giant P, and that's the P that's going to give me the trick. And if I do this, I'm going to wind up getting P inverse A. P is going to give me this, and that is going to be. And notice that. I notice I have 1, 1, 2, 3, and that corresponds to the 1, 1, 2, 3. Now here it just says 1, 2, 3, but since lambda 1 had two different eigenvalues, that's why it's 1, 1, and then 2, 3, and that is awesome. Let's do one fun example of a matrix which is not diagonalizable. And let's show that this matrix here, A, is not diagonalizable. So A is triangular. So the eigenvalues are the entries on the main diagonal, which is 1, lambda equals 1. And if I put A into reduced row echelon form, I get 0, 1, 0, 0, which means that means that x2 over from this 1 here tells me that x2 equals 0. And x1 could be, I'll make that t, so it could basically be anything. And that means every eigenvector winds up being x1, x2, which is t0, which is t times 1, 0. And hey, wait a second. I only see one eigenvector, or one linearly independent eigenvector. Actually, it's infinite because t can be any real number, but I only see one linearly independent eigenvector. So it must be that A is not diagonalizable, so we saw that right away. Isn't that cool? We didn't have to go through any kind of big tragedies and problems and so forth. Oops. So that's going to be the end. That's the end of this video. The next video is going to start from right here. But that concludes the video that we're doing, and we are. It's been awesome, and we'll see you next time. Bye, everybody. If yes, you'll receive it in the notification when the file is ready.